Good morning, everybody. My name is Johan. I am based at the University of Pretoria in the Department of Statistics. And I'm very happy to present to you our esteemed speaker for today, Professor Christophe Ley from the University in Luxembourg. Dr. Ley is an applied mathematician working in the field of statistics as well as data science, and works as an associate professor of applied statistics at the Department of Mathematics at the University of Luxembourg. He's also president of the European Association for Advanced Statistics Courses, president of the Luxembourg Statistical Society, and initiator of the International Network of Sports Training and Research in Data Science Methods for Analytics and Injury Prevention Group. Dr. Ley is currently an associate editor for the journals Annals of the Institute of Statistical Mathematics, Econometrics and Statistics and Society. And today's talk is called Statistics Meets Sports When Figures Are More Than Numbers. And Professor Ley, thank you for making yourself available to join us here, at least virtually in South Africa. And we're looking forward to hearing more about your talk.
Thank you very much, Johan. It is my pleasure to be here. Thanks for the invitation, for the kind introduction. So, as Johan correctly said, today I'm going to talk about when statistics meet sports. And for this endeavor, I have prepared the following program. So I will first provide a general introduction to sports analytics before explaining to you one particular example, namely how would you model with mathematics a football game. And then I'm using this to show you how you can predict tournaments, such as the World Cup 2018. And in the end, we'll finish with an outlook on how all this can be used in sports medicine for injury prevention. So first, sports analytics. Sports analytics has really taken off in the early 2000s. And this is the father of sports analytics, Billy Beane. So what has happened? Billy Beane was the boss of the Oakland Athletics, the general manager of the Oakland Athletics baseball team, which is a baseball team in the US. And it's a mediocre team. They did not have so much financial means. And in particular, in the season 2001, they did not really play well. So in that after season, Billy Beane was really shocked by their performance. So he decided we need to change something. And what he then did is that he has hired Yale economics graduate Peter Brandt in order to take over how the team should be built. And what this guy did is he used sabermetrics to hire players. Now, the word sabermetrics, likely none of you know what it means. It actually means data analytics for baseball. So baseball has its own term for data analytics. And he used this sabermetrics. So this implied that he did not hire players as one would usually do, but he was really looking at data, and that data would tell him, okay, if I take this player, should be not too expensive players given their limited budget. And so it was really a data-driven decision, how they hired players and consequently how they played. And this actually turned out to become a huge success. And this has revolutionized professional sport from then on, because other teams, other sports noticed, hey, data-driven methods, they really are helpful. And this has been made quite famous because first a book was written about Billy Beane and how he has revolutionized the sport by hiring these Yale economic graduates. And this book was called Moneyball, and it was later turned into a movie starring Brad Pitt. And this movie can be found online. So let me give you some more examples of what has followed up this first success. In basketball, there were the San Antonio Spurs. Their head coach, Greg Popovich, he has also been all about numbers. And he has figured out that when you look here on the left-hand side, this is the three-point line. So, whenever you are shooting outside of the three-point line, you are scoring 3 points instead of the usual 2 points. And he noticed that in the corners, the three-point line in the NBA actually is closer than on the rest of the floor. So his team started to shoot from there. And this has led to so you can see here in the early 2000s, this was the average percentage of three-point attempts from the corners in the NBA. So around 25, 26%, while the Spurs, they were 10 to 18% higher than the rest. And the Spurs, they were playing extremely well. So the other teams noticed this. And this has led to the so-called three-point revolution in basketball. So here you see over the seasons how the league average in three-point attempts has increased, the lowest value and also the highest value. We see a very clear improvement in terms of shooting 3 points. And this has, for those who know basketball, this has completely changed it. It's now a different game than it was in the 90s. This is an example of how much statistics now can be taken. On this basketball court, there are so many cameras that actually measure so many different aspects of the game, and new statistics based on the speed, the distance, how players are separated, and also ball possession. So it's a really completely new setting. Sports analytics provides so much new information, and tactics are so much built taking these data into account that it really shows how sports analytics have developed starting in the early 2000s until today. I give you one more example. This is from Formula One. This was the Monaco Grand Prix from 2005. The famous Kimi Räikkönen, the Finnish driver, he won the race. And this was done thanks to real-time computations by the analysts. So they were computing during the game how much fuel was there, how light the car would be when they have less fuel in, how much longer the tires would last. And also they were looking at wind resistance and other aspects. They were doing real-time computations. They came up with the best strategy when he should make a pit stop, and so he won the race. So what we can see, this success story clearly goes on, and it's becoming more and more of a success story. Every major professional sports team nowadays has sport analyticians. And it's not just for their tactics, but these sports analytical content, fans are eager for it. They want to know more about this, more about the statistics of their favorite sports. And there are plenty of websites nowadays that are dedicated to sports analytics. So for instance, there is the 538, which has been started by the famous Nate Silver. And this culminated in the creation of a completely new scientific journal in 2015, which is the Journal of Sport Analytics, where papers about sport analytics can now be published. So this showed you the setup and was meant to give you an idea of how the domain of sports analytics has been flourishing all over since the early 2000s. Now we will go on to the specific example of modeling a football game. So what is the main idea here? The idea is if we have two teams competing, we will assign to each team an overall strength parameter of that team. And with this strength parameter, we are going to model the score of the match. So is it a 3-1, is it a 2-0, a 0-5, and so on. And this score modeling, it's count data. So we are counting the number of goals over a fixed period of time. And we know count data, fixed period of time, a classical choice here is a Poisson distribution. Since we have two teams competing, we of course are then going to use a bivariate Poisson distribution. And the parameters of this Poisson distribution will depend on the differences of the strength of the two teams. Moreover, if one team plays at home, we will add a home effect for that home team. Of course, besides the Poisson, you have several other models that can be used. Many distinct models exist, and actually, as one can see, it is lucky that the simplest models turn out to be the best. I will come back later on this. Let me now become more concrete and show you this bivariate Poisson model. So suppose that we have team I playing against team J in match M. So I'm writing YIJM as the number of goals that team I scores against that team J during this match M. And we suppose that we have N teams and M, a total of capital M matches being played. And I'm writing the Poisson parameters lambda IJM stands for the number of expected goals that I would score against J, and similarly lambda GIM, number of goals of J against I. So with this, we can model the final score. Let's say that the match ended on X goals for team I, Y goals for team J. So we want to express the probability of such an ending, and it is given by this formula here, which is simply the bivariate Poisson distribution. So what you can see here is that we have the two classical Poisson parameters plus a covariance parameter. This covariance parameter measures indeed the covariance between the two teams, the interaction between the teams. If this parameter is equal to 0, then this part disappears, and also this sum, the sum simply becomes 1. And so if you forget about all this part here, what is left is simply the product of two independent Poisson distributions. So this special case is also contained in this more general model. So this is the formula. And now, of course, how are the strength parameters being taken into account? So I am writing Ri, the playing strength of team I. And then they are brought into these Poisson parameters in the following way. So we define the logarithm of lambda IJM as some intercept basic parameter beta 0 plus then the difference between Ri and Rj. Plus here we are adding if team I plays at home, so we have this indicator function, and then we have our home effect parameter. We put it belonging to R. One believes that in general playing at home, of course, should be an advantage, but it could also be that this is not the case for in general. So this is why we do not restrict it to be necessarily positive. How can you understand this basic this intercept parameter? Suppose that we have two teams that are equally strong, so this is equal to 0, and then there is no home effect, where also this falls down. So beta 0 then is the parameter that defines the average number of goals that will be scored in a game of two teams that are really of equal strength. Okay, so this is how we are modeling the score in a football game between two teams, I and J, and we see the parameters at play here are this intercept, the home effect, and then the playing strength of the different teams, and also this covariance parameter. Now, how would we estimate this? So we consider a period of M matches. This is why I'm presenting it with several matches. We, of course, have several teams that play against each other over these matches. And what we do is we simply estimate the parameters by means of maximum likelihood. So we assume here that the matches are independent. And actually, this is not just an assumption that comes out of nowhere, but studies have been done, especially in tennis, showing that different points are to be considered independent, although one would not think so. But if a team, because teams sometimes have a winning streak, but then all of a sudden they also start to lose. And so it has been proven that the assumption of independence actually holds, because even if a team is strong at a moment, it still can lose out of nowhere. And so this is why we are making this assumption here of independence. So over the M teams we have here, in match M, we have that YIJM, YJM is the actual score of that match between the teams playing in this match. So, and like this, you simply estimate numerically the parameters. Now you can further fine-tune this by adding here an exponent, a weight. And this weight is a so-called time decay parameter, because you might want to say, if I want to measure the strength of my teams now, and I have matches played over the past 2 years, then of course the matches that are played more recently, they should get more weight than matches that are played a long time ago. So you can add such a decaying weight function that depends on the number of days ago that a match has been played. And well, what do you get from this? Of course, in the end, we will have estimated the playing strength of all the teams, and this allows us to rank them. So we obtain here, with such a modeling, we obtain a ranking of teams based on their current strength. And this can be very interesting for various proposals. And one application here is the FIFA ranking of national teams. So, you know, when national teams are playing, as they did last week, when national teams are playing, then there is also the FIFA ranking that is being established based on their results. The aim of this FIFA ranking is precisely to reflect a team's current strength, because this FIFA ranking is used for the seating at subsequent tournaments. So it is important to have a ranking that reflects well how strong a team is. And here I'm showing you an example of the FIFA ranking is not always optimal. And it has been changed in 2018. Since then, it's better because they noticed that there were problems. But here I'm showing you one example in 2013 where the then used FIFA ranking was not ideal. So you see here in red, this is the FIFA ranking of Scotland over a period of 1 year. you see that it's dramatically changing from month to month. It is not stable at all. And this is not even due to Scotland playing so many matches. You would have the feeling that they are playing all the time matches, but it's not the case. There is a huge fluctuation, which was a drawback of the ranking at that time. And here in blue, you see what the ranking would be if you were using such a statistical method based on the bivariate Poisson distribution. And you see that it's much smoother. These fluctuations, they do not occur. I should just explain here, half period, what does that mean? This says that our decaying function gives half the weight of a game played to half a weight of a game played today to a game that is played 3 years ago. So the half period is the time whenever we halven the importance of a game. Why did we use this bivariate Poisson model in particular? And this is what I said I would come back on. It is a model that was proposed in 1982 by Maher. And in a paper with my PhD student Hans van Eetvelde, we actually were comparing various models and we were showing the superiority of the model, not just in terms of facility, but also in terms of reflecting well a team's current strength. So that is why I say the simplest models, fortunately, turned out to be the best. Now, what else can you do with this ranking? Well, you can use it in order to predict big tournaments. And now I'm going to present you how we use this in order to make a prediction for the World Cup 2018. I'm not going to show results for the European Championships 2020, which actually happened in 2021. There we also did predictions, but that European Championship was a bit different in the sense that it was still a little bit under the impact of COVID. And so I think that this one is more accurate. We also made a prediction of the female World Cup 2019, which I could also have shown, but I decided to show you the very first time that we made such a prediction, which was for the male World Cup 2018, because it was then that the idea was newly shown. So in this paper, we have compared the different models, and we also then showed how to estimate these team strengths. So the estimation that I showed here, this method, we discussed it in all detail in our paper. And these team strengths, you can also call them abilities. And what we then did in this 2019 paper, this is a paper that we had actually done prior to the World Cup 2018, where we have done our predictions for that World Cup. So here, what we did is that we have used the strength of the teams, which we call abilities, we have used them actually as a predictor in a machine learning model. So we have used a random forest, which is a classical machine learning method, where you can make predictions between two teams by taking various factors into account. On the next slide, I'm going to show you these various factors. But we used here as a special feature, we used these estimated abilities. And that's why we call this a hybrid random forest, because we are not just using observations that we can observe at the start of the World Cup, so the classical features, but also we were using these estimated abilities, which are not observable directly, but which are estimates. So they are enhanced by a special by the uncertainty that we have typically associated with estimators. This is why this is a different type of random forest, because we combine a statistical estimate with a random forest. So here are the overall covariates that we have been using for the World Cup. We were looking at economic factors of the countries, such as the gross domestic product per capita and the population size. We were looking at sportive factors, so bookmakers' odds prior to the World Cup, their FIFA ranking, and also the ELO ranking, which has actually just after 2018, the FIFA ranking that has been used till then has been replaced by this ELO ranking. And so we decided, let's use both rankings here as sportive factors. And we were also using these ability parameters. We were also looking at home advantage. So who is the host of the World Cup? Does a team play on the same continent as the host? Because traditionally, this is known to be an advantage. And what is the confederation? Factors also describing a team structure, very important. We were looking at the average age. We were looking at the maximum number of teammates, because if many players in the national team play together in the club, of course, they know how to play together. we were looking at the number of Champions League and Europa League players of the prior season, because it's also logical. If you have players that play at strong teams, they will appear in the Champions League, and players that play in strong teams are synonym of a strong team. So this is why we use this. And also we use the number of players that play abroad. Are there many players that play abroad or in the country of their national team? And finally, also, we were looking at factors that describe a team's coach, such as his age, nationality, and tenure. Interesting, since we are looking at two teams playing against each other, all these variables will be incorporated in our random forest as differences between the teams. So let me show you this on an example. This is an example from the World Cup 2002. So here we have, for instance, France playing against Uruguay. And in this case, so these were the values of France and Uruguay. The average age 28.3, 25.3. The FIFA ranking of France was, they were the best at that time. So it was 1 against 24. And these were the odds, set odds, and so on. We then, when we were running the random forest for France, for the number of goals that France would score against Uruguay, we would use an age difference of 3, a rank difference of -23, odds set difference of this, and so on. While for Uruguay, it would be -3, +23, and -0.14, and so on. So now you see how we incorporate these differences. And now, how are we going to use these covariates? We want to predict the number of goals. And the question is, how do we do this? Well, I already said it. We do it by means of a random forest. And we use this random forest. Of course, it needs to be trained. So we trained it on the previous World Cups from 2002 till 2014. One may ask, why not prior to 2002? It's not because the earlier World Cups are not reflective. It's just that at that time, we cannot retrieve all the covariates prior to World Cups 98, 94, and so on. We just do not have the data. This is why we start in 2002. Now, let me explain you, for those who perhaps are not familiar with random forests, how a random forest actually works. The principle of a random forest is that we are aggregating a large number of decision trees. So decision trees, I will also explain you how decision trees work, but each decision tree gives us an answer. And for this, we can have two types of decision trees: classification, if it's a yes/no answer, or a regression, if it is a continuous number. And we are aggregating them all together. So, as I said, the final prediction will be an aggregation of all the trees. In case of a classification, yes/no, we will go for a majority vote. Was the majority of the trees for a yes or for a no? We go with the majority. And for regression, each tree giving us a continuous number, we simply average these numbers. And this is going to be our final regression example. Now, in our case, we want to predict the number of goals that each team scores against the other. So obviously, this is a regression problem. So now we are interested in regression decision trees. So for such a tree, let me first show you an example, a very simple example. Here, I'm just using a short tree where we just use two covariates. So this is an example of what a trained regression tree looks like. So the very first split in the tree occurs at the level of the FIFA ranking. So what we see here is this is from the perspective of the team for which we want to predict the goal. If the difference in ranking is smaller than -15, you have to think for a moment, what does that mean? Smaller than -15. I said the ranking of the first, again, minus the ranking of the second. So this means if the team we are looking at is 15 rankings stronger than the other team. If that is the case, then, okay, we already land in this end node. And it is from this node that we take the decision, which means we are looking at all our matches that are in this node, and we take the average of the goals that teams have scored which land in this node. And just for the interest, you might see here, there are historical matches where 8 goals have been scored. These 8 goals were the 2002 World Cup, where Germany has been able to beat Saudi Arabia 8-0 in that World Cup. If the difference between the two teams is smaller than 15, then we go on this side of the random forest. We look at another predictor, which is here the odds set odds, and either we land here or we land there. Here again is this is 7 goals. This is the famous 7-1 of Germany against Brazil. I cannot tell you by mind the other results here, but you might perhaps, for those who are familiar with this, you might recognize it. So it's a top, you start on the top, you look at the covariates, and then you land on either of them. And depending on where you land, this is the prediction that the random forest will give for the average number of goals for that team. So here I'm just repeating it is just written how it is built up. So for each tree on top, you search for the split that leads to the largest difference between the partitions. And the goal is that observations that lie inside such a partition are as similar as possible, of course. So that's for one such decision tree. Now, what is special with random forests? Well, we are building different regression trees. And the name random forest suggests that there is some randomization occurring. And actually, there are two types of randomizations that are being done. First, why? Well, because, good, we now have our data and we build a regression tree. If I use, again, my data and I build a regression tree, it will, of course, be the same. So why would we then aggregate them? It is here where the randomization becomes important. For each tree, we look at a different data set. Actually, we are looking at bootstrap samples. So we are bootstrapping samples from our original sample. And so each tree already is trained on a different sample. But there is one more level of randomization that is being done. Namely, it could be that some predictors are very dominant. And so each tree would have this predictor or this feature on top of it. But we want to have trees that can also be different. So at each split in the tree that we consider, we randomize the predictors, and we only choose a subset of the total amount of the total number of predictors at each split. So when a split is performed, we do not consider all of the predictors, but just a random subsample. And this ensures that not always the same predictors will end up on top of a tree. So the single trees, by their nature, they are nearly unbiased, but they have a high variance. And the idea of random forest of averaging the trees actually is reducing this bias. So it's reducing this variance. So what we get in the end by using random forest, you get a prediction with low bias plus a reduced variance. This is why such an ensemble method as random forest is so strong. Now in football, of course, as I already said it, we wish to predict the number of goals. So this is our response variable. And yeah, so we get different predictions. And now the prediction that we get, let's say 2.2 goals, for instance, we will not just say, okay, this is the number of goals that we predict now for this team. What we rather do is that this predicted value, we take it as the event rate of a Poisson distribution. And then we have this for both teams. We have their predicted numbers. And so we have then, with these Poisson distributions, we are then simulating the outcome of the game. So we are simulating how likely, and we can calculate how likely it is that each team is going to win. So the random forest gives us the predictor, lambda, as the average amount of goals that a team is going to score. And then with this, we are using a Poisson distribution to measure the probabilities, to calculate the probabilities of the final outcome. This is how we are going to predict the probabilities of each match. So now you know how we're doing it for a match. How are we going to do this for the entire World Cup? Well, at the predictors, all of the predictors except for the abilities, they are taken the last week before the tournament starts. So the predictors that you see here, all of them except the one in red, they are taken 1 week prior to the competition. That's when we take the measurements. And how are we going to do it with the abilities? Well, they are of course estimated via the bivariate Poisson model that I've shown you. And to this end, for the 2008 World Cup, we actually chose 8 years of matches preceding the World Cup, with of course a decaying function, giving more weight to the more recent matches. So in our case, these were 7,000 matches from which we estimated the abilities of the teams. Okay, so with all this given, we are able to do two things. One, we are able to, for each new match that comes, we can calculate the probabilities for first team winning, second team winning, or draw. But what we could also do prior to the World Cup, we could simulate the World Cup 100,000 times and then this could give us overall predictions prior to the start of the World Cup. And of course, at knockout stages, we would do this by taking special steps, such as if there is a draw, then we would make a coin toss. Now, what I'm showing you here is something that is very important, because I told you that, well, classically in machine learning, you are giving the outcome, the prediction. That's fine. That's what they are made for. But of course, from this, you cannot get any insight. It's like a black box. So it is very important and interesting to actually be able to know which predictors really now had an impact on the outcome and which not. And to this end, I'm showing you here the importance of all the covariates. So this importance is based on the training. As I said, we trained our data on the previous World Cups. And during this training, or the classical training test and so on, during this training, we could measure the importance that each covariate had on the final outcomes. How do you do this? Well, by taking each component at once. So, oh wait, let me restart. How do you do this? Well, first of all, you can, during the training phase, you can measure the performance of the random forest, no? With the training test phenomenon. So you are going to measure the performance by taking all the predictors into account. And now, in order to know how important a given predictor is, say the abilities, what we do is that we train again the model, we check how accurate the model is during the training phase, but this time the abilities, they are being shuffled, which means we render them meaningless. That is, the ability that a certain team has, it is no more assigned to that team, but it is randomly assigned to any other team. And we do this random assignment all the time, which implies that the abilities then, actually they are still in the model, but they are meaningless. And we do this then also for ELO, for rank. So for basically each predictor, we annihilate its impact. And then we look at how much accuracy do we still have. And so in the end, you can look here at the mean decrease in accuracy by taking out each component. And this clearly shows that the abilities are by far the parameter that has the strongest impact, followed by the ELO ranking, the FIFA ranking. So all the rankings, the sporting factors are the strongest. We actually see that some predictors have a negative impact. So the population has a negative impact. How is that possible? Well, you have some countries such as China who participated in the World Cup 2002. They were not very strong at that World Cup. During the time now, they are doing everything to improve themselves, and they are indeed improving. But at that time, they really played a bad World Cup, which is why China is an example where the size was not proportional to the size was not helping. On the other hand, you have countries like Belgium or Iceland, which are very small, yet they were able to play very well. This can explain why population here is negatively affecting the outcome. Of course, a country like my country, Luxembourg, over all these years, we were never in the World Cup. So in a sense, we are truly reflecting that small population means small results in soccer. But this gives you an idea of how good the individual predictors are doing. Now, let me show you how our predictions were. So here I give you from our simulations the most probable group stages. So we could see for each group, these were the teams that were predicted to advance. And so from these 16 teams, the model was able to predict correctly 14 teams that would advance to the next round. The two teams where we failed were Poland and Germany, but Germany really was a surprise that as title holder, they were not able to advance to the next stage. Now, this being said, if you look at the history, it actually happens that over the past World Cups, always the title holders played badly in the subsequent World Cup. Might be a saturation effect, I don't know. But so that's where, those were the two mistakes that the model did. Otherwise, we got 14 out of 16 correct. Here I'm showing you a performance measure. What is the probability that we gave to the winner to win? And so we took the average of all these probabilities. Classification rate is how correct were we in classifying winner, draw, winner. And RPS this is a loss function that you want to have as small as possible. So the first two should be as big as possible, this one as small as possible. And you can see that in all three, our model was actually able to outperform the bookmakers, which is extremely strong because the bookmakers have extremely good models. And just a word about the classification rate. One should not compare this to 50% because we have a three-way outcome. So you have to compare this to 33% of random guessing. We then also took part in an international forecast competition, FIFAexpert.com. And we played under the name of one of our authors because we had to do it fast. We played under the name of Andreas Groll. We ended up second. And until after the semifinals, we were first, but then another artificial intelligence actually was able to beat us by a small edge. We also compared ourselves to human players. So here, this was a game called, a competition called Kick Tip, where everybody was predicting the outcome of a match, and we were also using our stats model. And clearly, the model was far better than the individual players. Now, let me finish here with an outlook on how this prediction can be used in sports medicine. So what could be a main goal in sports medicine? Well, injury prevention, which means estimate an athlete's risk to suffer from an injury based on various predictors, such as biometric predictors, the training that they are doing, how much sleep they get. This can be questionnaire. These data can be from questionnaires. They can be from wearable sensors that people wear, from very different sources. So the challenges in this is that, well, there is a difference between the various sports. You play soccer is different than if you play tennis. Then there is a difference between men and women, also an important difference. There is a difference between professional and recreational athletes. So for all these different settings, we would like to come up with an estimation of an athlete's risk to suffer from an injury. And a big difficulty here is that sports data, they happen to be massive. There are a lot of data available. As I said, just think of the wearable sensors, you will get a lot of different data. They are non-standard. They are also incomplete. Very often you have missing data here and there. They are unstructured. You get tons of data which appear under various forms. They can be noisy as, yeah, is this really what you measure? Have the athletes well responded to the different questionnaires? And then, as I said, they come from very different sources. Wearable data, data that you just measure every day, questionnaire data, and so on. And the difference between sports really makes difficult because you get so many different aspects that you have to look at. And then, of course, you also have a big difference if you look at the Olympic sports versus the Paralympic sports, because in the Paralympic sports, you even have to take into account various other aspects. So also there, for instance, if you think about power chair hockey, and we have an expert of power chair hockey here in the audience, there are so many different aspects that you have to look at. It's played in a quite different way from classical hockey, and you have to take into account. You cannot always just change the players, but there is a system depending on the level of handicap that the athletes have. You must always stay below a certain maximum number of points. So each athlete is given a point for the handicap that they have, and the sum of the players on the pitch with respect to these handicap points must not exceed a certain level. So this also is being added. So it's really challenging. And then injury risk is multi-causal. There can be so many different reasons why you injure yourself. And of course, there is a dynamic interplay between internal factors, the age of an athlete, previous injury. Athletes that have suffered from a previous injury, they are much more likely to sustain a new injury than athletes who have not been injured. And of course, there are also the external factors, such as the exposure or the materials that are being used. There are so many different parameters. And then there is the contact during sports. So many different things that you have to take into account. And this is what we would like to tackle here by using this machine learning technique, by combining it with statistical estimates, but also taking into account causality questions. This is how we wish to tackle the important issue of injury prevention in sports. And what is very important is that the end users who are using it, the coaches, the athletes, they need data-driven solutions that are user-friendly. We cannot just give them, oh, look, this is the outcome. This is the outcome of our data. Now do something with it. No, they must be able to understand it. And so we cannot just have a black box machine learning algorithm. We must have an algorithm where we understand what are the driving factors. If I say this athlete is at 60% risk of being injured, we must be able to say what are the main driving factors behind these 60%. And that is why we need interpretability in the machine learning. And I'm ending here just by showing you, this is the AS Training website that Johan has alluded to. So our sports, training and research in data science methods for analytics and injury prevention group. You might wish to visit it. Here you see the different members of our group. And you can also see in the activities prior seminars that we had. By the way, today at 12, we are having such a seminar. So whoever is interested, you can just let me know and I will send you the link to it. Thank you very much for your attention.
Thank you, Christophe. I think this is incredibly valuable. I think it is incredibly interesting to see the application and move of the theoretical underpinnings within something that so many of us enjoy, watching in our free time, and to amalgamate our thoughts into watching sports and thinking more about how all of these theoretical underpinnings work together. I think it's incredibly interesting. So thank you for a very insightful talk. I want to ask the audience let us start with everybody who's here joining us online. I think I just saw a hand from someone. I have here Dr. van Staden. Paul, please unmute yourself. Please go ahead and ask a question.
Thank you so much, Johan. And I want to thank the speaker. This was truly an exceptional presentation. Well done. This is really, and if you go back to your previous slide, that last bullet is actually sums it up brilliantly, because I think that is unfortunately what I've seen in many sports happening. I can give examples like rugby and cricket, which you might not be so familiar with, but those are sports that are very popular in Commonwealth countries like South Africa. And there they have struggled to incorporate many of the very good things that have been published in journals, because it's not always user-friendly for the coaches. So it might be statistically and data science very applicable, but yeah. I do have a question for you regarding home advantage.
Yes.
Because there are different ways of looking at home advantage. So I'm going to give an example. Manchester City plays against Manchester United. They play at Old Trafford. The players from Man City, it's an away game, but you presume they are sleeping at home in their own bed and not somewhere else. So yes, it's not their own stadium, but yeah. In contrast, I'm sorry, I don't know soccer very well, but I know how to use Professor Google. So I quickly Googled. F91 Dudelanne has to play from Luxembourg, has to play against Qarabakh from Azerbaijan in Europa League. And the away game is quite a distance away, and now away is really away. Have you looked at those kind of dynamics within home and away or not?
That is an excellent question. And I also thank you for your comments before about this end users, the importance of this. No, we actually have not looked at this, but this is something that with a PhD student of mine, we now wish to actually incorporate the actual distance of how much you have to travel, because I totally agree with you. This is an important aspect. If you have to travel far, the home advantage might even be stronger, because the teams can be very tired from this, and the situation, the surroundings can be very different. So no, we have not looked at this. This is for this, it's really a simpler model where we just aggregate everything into one home effect. But this is something that we wish to incorporate for the future. Yes, absolutely.
Thanks. And if you could please, or not possible maybe, but share the link for what happens at 12 o'clock. I will gladly reschedule my day to attend.
Sure.
Maybe you can put it in the chat line. I don't know if that's possible.
I will put it. No, that is possible. I will put it in the chat.
Yeah. Thanks so much. Thanks, Johan.
Thank you, Paul. Is there anybody else who maybe has a question or a point of reflection or a curiosity that they wish to raise? I'd like to take this opportunity to thank you, Christophe, for giving us a very refreshing seminar in general. I think we've all taken something from this, even if this might not be some of our, direct research focus areas, but the applicability, and especially when you mention here about the sports medicine, is impactful. It is one of those developments and research foci, I think, that has a broad-based effect and impact that is very interesting. I want to thank you for your time and your expertise on behalf of the CoE. I would like to thank our CoE team on the ground at WITS for making sure that everything runs smoothly. And I would like to thank everybody who made the time to participate in today's session. And I want to give us just another minute if you would like to copy and paste the link and the title of the session starting in, at this point, according to my watch, 39 minutes, yep. Then you can save that quickly. Other than that, allow me to wrap up the session. I thank you once again. And if there's no further information or comments from the CoE-MaSS team on the ground, I would like to bring the seminar to a close. Thank you, Christophe, and everybody once again.
Thank you very much. Have a nice day.